Okay. Hello, everyone. Thank you very much for having me here. So I'm happy to tell you something about parking functions today. This is joint work with Martin Ruby at TU Wayne. Okay, so first a brief intro. Parking functions have been an active area of research ever since Cohen and Weiss raised this phenomenon about parking. So the idea is that there is there is a street parking situation where a line of n cars can enter from one side of the street one by one, and each car has a preferred preference spot. And if the preferred preference spot is taken, the car will drive forward to park. Well, if it can indeed find a parking spot in the end, and every car can do that, then this is called a parking function. And this phenomenon has been generalized to multiple different situations, but this is a classical situation. And so we usually denote a parking function by pi. It's a generalization of permutation, as we will see later. So here is a graphical representation. We have a one-way street, and then with n spots, and then we have n cars. And for n equals 1, you see when the preference is 1 is the only possibility. And for n equals 2, we have more possibilities.
Sorry,
I think the slides are.
Huh? Sorry?
The slides are not moving.
Oh, really? They're moving on my end. Is there anything I can do?
Maybe you have to
You
share
have full screen, and full screen is stopping the slides from moving for us.
Oh, okay. Let me see. Is it better?
Yes.
Okay. Yeah, sorry, not very tech savvy. Okay, sorry. Okay, so for n equals 2, this is we have 3 possibilities, 1, 1, 1, 2, and 2, 1. And for n equals 3, we have these many possibilities. And then people got interested in this, and they were asking, okay, so is there a more apparent way to see whether this is a parking function or not? And then they found that we could just characterize it using a pigeonhole principle. And this is a pigeonhole principle written here, where we see that the number of cars with preference less than or equal to I has to be greater than or equal to I for every I. And then from here, more things can be derived, and people found that the number of parking functions for length n is n plus 1 to the n minus 1. And this is a magical number because it coincides with the cardinality of many other combinatorial objects. And also from the pigeonhole principle, we can conclude that parking functions are invariant under permutation of the cars. So let's see. So there are many directions you can investigate when it comes to parking functions. For this talk, we are going to concentrate on one particular direction that is about the fixed points and cycles in the digraph representation of parking functions. So what is a digraph representation? It is defined similarly as in the digraph representation of many other like permutations or in general mappings. So what we do is that we will draw a directed graph, and the directed edge is from I to pi I for every I. And then we will see that the digraph will consist of disjoint components, and each component will consist of a cycle along with tree components attached to the vertices of the cycle. And the permutation is a special case of such digraph representation, because all the components will be trivial in the sense that you don't see any tree components. So in the next slide, I give you a simulation of a parking function on 20 vertices. And I choose this specific one because it has some nice features. We see that it has 3 components, and one component is very trivial. It's a fixed point. The other component has a pair of vertices and also one tree branch, well, just an edge attached to it. And then another tree, a component is more substantial. It has a cycle and different trees attached to the different vertices of the cycle. Okay. All right. So from here, we see that there's something difficult about studying these objects because they do not satisfy nice exchangeability properties. By exchangeability, I just mean that if you randomly switch the vertices on the digraph representation of a parting function, you don't necessarily get a parting function back. This is different from permutations and also different from mappings, because for permutation and mapping, if you randomly switch the vertices, you can always get another permutation or mapping back. So, but we notice that if you switch the tree components, I mean, the trees attached with the vertices altogether, you still get something back. So this enables the cycle structure study for these objects. Sorry, I will answer the question later. For example, here we see a parting function on the top graph, and we switch the trees together with the vertices, we get another parting function back. Sorry. Okay, so now let's come to the main object of study here, the count of fixed points. So we say that index I is a fixed point of the parting function if pi I equals I, and the fixed point of a parting function is a vertex with a self loop, as we saw in the simulation earlier. And fixed points are simply one cycles. It turns out that the number of parting functions of length n with k fixed points is exactly given by this formula. And I will give a quick outline of the proof of this formula in a minute. But before that, let me talk about some related OEIS sequences of this. So because there is n and there is k, and then we put in different k's together with the n's, and we see that it pops up in the different OEIS sequences. So for k equals 0, we see something, k equals 1, and then n minus 2, n minus 1, and for k equals n, it's like all the points are fixed. So, sorry, for k equals n, yeah, this is what we saw. And then the parting function will have to be 1, 2, up to n. And then for the middle case, we don't find them in the OEIS sequences. So there are many interesting bijections waiting to be studied, like why for different case. We will see all these different OEIS sequences. And here is an outline of a proof. So the proof at the start it's actually quite classical. So we are just going to use the inclusion-exclusion property for parting functions. When we have k fixed points, we will have to choose k indices so that they are fixed points. And then the remaining indices, we need to state that they are not fixed points. That's why you see the intersection here and then the latter intersection. And then we are going to use inclusion, exclusion to expand them into a more complicated formula. And then the next step, we use the permutation symmetry of the parting coordinates so that we change all the indices back to, back to the initial indices. And then I give a shorthand notation of the big cardinality. Okay, so for this, we will then try to count the cardinality of the big thing at the previous slide. And for this, we use Pollard's argument. So Pollard's argument was used to prove the cardinality of parting functions is n plus 1 to the n minus 1. It's a very ingenious argument. It says that because we see a product here, so probably we could just assign n cars on a circle, and then every car has n plus 1 preference spots. And then we will do a rotation, and then only one out of n plus 1 rotations gives us a valid parking function. And from this, we are thinking, okay, so if we look at the previous slide, pi 1 up to pi k plus L are pairwise distinct. So we need to choose k plus L distinct points on the circle. And then that's why we have n plus 1 choose k plus L, and all the other car preferences, it could be any of the n plus 1 choices. And then, yeah, some other combinatorics, we get the formula. And then the last step of this is simplification using binomial theorem, and then just expansion, looking at it backwards, and then we get the final result. And then from here, it's also easy to see a generating function for fixed points. It's given by this formula. Okay, so next, I will show you how do we generalize the result to count of cycles. To do count of cycles, actually it uses an idea that Richard used in his previous talk. Instead of looking at choosing one point, we will choose a tuple of points. So, but first here is a formula. The number of parking functions of length n with k m cycles is given by this more complicated looking formula. And a cycle just means a cycle in the digraph representation of the parking function. Sorry. Okay, so I also wanted to point out that the fixed point formula we saw earlier is just a special case of this, even though at first sight it doesn't look like a special case, but like if you just manipulate the formula a little bit, it is a special case. And then also like for these formulas, asymptotically, they are the same as number of mappings and permutations, but the error terms are different. From there, we could derive a range of probability results from there. And then there are also generalized formulas for in the combinatorics setting. Right. So here is a quick outline of the proof. And like I said, the idea is that instead of taking one point, we are choosing a tuple of points on the circle in Pollock's argument, and then together with some other arguments using permutation of symmetry and other things. Okay. All right, so last thing I wanted to mention is that all the formulas presented here have generalizations in prime parking functions, and prime parking functions is a prototype object of study because they pop up nicely in parking functions, symmetric functions. Like prime parking functions means that at least j plus 1 cars have a parking preference in the first j parking spots for every j from 1 to n minus 1. And then, yeah, so you see for n equals 1, n equals 2, n equals 3, the prime parking functions are a smaller subset of the general parking functions. And all results presented here have a corresponding prime version. And here is a prime version for all the results. And you can see that most of the time we just need to change n plus 1 to n minus 1 at some respective places. And then they also have nice asymptotic formulas and so on. Okay. Yeah, this is my last slide. Thank you very much.